So welcome to afternoon session of Third International Hydrogen Energy Congress and Exhibitions. So our first speaker will be Mehtap Akgün from Aksaray University. And the presentation title that she is going to talk about is that C-type structural stability analysis for copper sulfide solid crystal. So now we will start this presentation. Do we have the speaker now? Mehtap Akgün.
I hear.
Yes. I think they are uploading your presentation. Yes.
Hi, my name is Mehtap Akgün. I am a PhD student in the Department of Physics at Aksaray University. Our study concerns structural analysis of the copper 1 sulfide compound. I will give a short information about the compound. Then I will explain the methods we use it. Next, I will present the obtained results. And finally, I would like to brief conclusion and share the future study plan. Why copper sulfide materials? Copper sulfide has a simple composition consisting of two copper atoms and one sulfur atoms in a primitive site, but is a complex material. Due to the high mobility of copper within the sulfur sublattice, the structural phase relations are complex even at ambient conditions and has therefore been in the focus of numerous studies since 1926. Copper sulfide are a family of compounds with outstanding physical properties such as ion conductivity, superconductivity, thermoelectricity, p-type semiconductivity, and fast switchable phase transition, resulting in a wide field of potential industrial applications reaching from the film solar cell absorbers to resistor switching device. The main focus of our research to predict the most favorable copper 1 sulfide phase and then study its stability. We use DFT to predict the most favorable phase and then study their mechanical and vibrational stability. We studied 33 possible A to B type structure by gathering information from various resources. All structures calculated in the study are shown in the table. Looking at the table, most energetically stable structure is given first, and the other structures are listed according to their energetic states. The mechanical and vibrational stability of all structures were also calculated. As a result of optimization calculations, 3 from 39 C-type structures were found to mechanically and vibrationally stable. Hereafter, I will only focus the 3 structure and experimental ones. All calculations have been carried out by using the Vienna ab initio simulation package based on the density functional theory. Simulation parameters: cutoff energy 520 electron volts, pseudopotential PBA, exchange correlation energy GJ, K points are in table. We optimized the lattice constant in internal parameters to obtain a relaxed structure and then calculate other physical properties. Structural properties obtained as a result of calculations are given in the table. From this data, we can say that we have identified 3 new synthesizable structures that are not yet known for the copper 1 sulfide crystal. The stress strain method implemented in VASP code was used to predict the second order elastic constants for all considered structures. The calculated elastic constants are satisfy the related mechanical stability so that these compounds are mechanically stable. This shows that into the experimentally null structures, the copper-1 sulfide crystal can be synthesized in our newly proposed structures. In order to use time efficiently, I will only list for the energetically most favorable structure results in the next slides. The mechanical properties such as bulk modulus, Young modulus, shear modulus, and Poisson rate, which are functions of the elastic constant, are calculated by using Voigt-Roy's wheel. From the results, we could judge the copper-1 sulfides in C21 structure, has soft nature, ionic bonding, and ductile. We were calculated the electronic bond structure of C21 type copper-1 sulfide compound and give in figure. It's seen that copper-1 sulfide has an indirect bond gap with the value of 0.2039 electron volt and its valence band maximum and the conduction band minimum occur at the gamma points. All defined stable structure exhibits a semiconductor character. The present phonon frequencies of all compounds are calculated using a supercell approach by the phono-P code, uses the DFPT. The figure shows the phonon dispersion curves and corresponding density of states copper-1 sulfides in C21 structure. The calculated phonon dispersion curves do not contain salt mode at any vectors, which confirms the stability of copper-1 sulfide in C21 structure. Conclusion: in summary, we have performed the first principle total energy calculation for copper-1 sulfide using the plane wave pseudopotential approach to density functional theory within the GGA. The copper-1 sulfide compound was investigated in different C-type structures, and it was found to be mechanically and dynamically stable in 3 phases. For all structures copper-1 sulfide, the Gb ratio is 0.5 and ionic bond is dominant. It is supported by the Poisson rate of about 0.25. The Bg ratio is greater than 1.75 and the ductile character is dominant. We hope that our other predict results will be serving as a reliable reference for the future experimental and theoretical studies. Our studies are ongoing. We continue to calculate thermodynamic properties, optical properties, magnetic properties, and other properties. To study of universal structural analysis of C-type copper-1 sulfide compound, we will continue with USPX method. Thank you for your attention.
Thank you for your presentation. Are there any questions? Oh, I guess there aren't. So our next presentation is going to be given by Hüseyin Tavukçu from Gazi University, Ankara. The presentation title is The Effect of Doping of Rare Earth Elements on Dehydrogenation Efficiency for Vanadium dihydrate compounds.
Dear Chair, this speaker is joining with a video.
Yes, okay.
Hello. Firstly, thank you for coming, everyone. Before I start, let me tell you something about myself. My name is Hussein. I'm from Turkey. I am a graduate student at Gazi University, and at the same time, I am physics teacher in a public school in Turkey. I am working on solid-state physics and density function theory. Today, I will tell you effect of doping of the rare earth elements on the hydrogenation efficiency for VH compounds. So my presentation will be about hydrogen energy. The content of the presentation will be as follows. Motivation, hydrogen atom, computational details, results and discussion, structural, electronic, and mechanical properties, and conclusions. Okay, motivation. And the researchers for development of the technologies of clean renewable energy have increased due to increasing air pollution and global warming problems. To provide our future energy demands, hydrogen is searched as one of the major energy carriers in developing new strategies. Because hydrogen does not produce any harmful gases, it has been considered as one of the most promising energy source. Materials-based solid-state storage of hydrogen, including the use of metal hydrides and complex hydrides, have been investigated densely for it has high hydrogen density and safety. However, the viability of technologies for hydrogen production, storage, and onboard usage are still under investigations. In contrast to storing hydrogen in molecular form, it can also be stored as atomic hydrogen in metals and intermediate compounds, leading to higher volumetric density. Advantageously, MH provide relatively safe storage at ambient pressure conditions compared to compressed hydrogen gas, and these materials can therefore be handled relatively easily. Vanadium-based alloy has been treated as an excellent hydrogen storage material because of its high hydrogen storage capacity and fast dehydrogenation kinetics at moderate conditions. During the dehydrogenation process, vanadium alloys have two plateaus corresponding to the reaction between V and VH1X, VH1X and VH2X. It has been shown that these two plateau pressures alter differently depending on the type and concentration of the pants. During of rare earth elements can improve the efficiency of hydrogen storage material in two ways. One of them is that larger size of Ra and uh, a larger size of Ra depends increase the unit cell volume and thus increase the VH bond length, indicating that these results decrease the VH correlation and disruption temperature. Second one is higher volume of Ra elements doped unit cell of VH2 may store high hydrogen at interstitial space, showing high specific capacity more than in pure VH2. Okay, we see we see here properties of the hydrogen atom. Important isotopes 1H and 2H. Electron configuration 1s1. Density 0.000082. Atom radius 1.10 angstrom. Electron affinity 72.769. Electronegativity 2.20. Year of discovery 1766. How is the hydrogen storage? Hydrogen can be stored either as a gas or as a liquid. Hydrogen gas storage typical requires the use of high pressure tanks, while liquid hydrogen storage requires cryogenic temperatures to prevent it boiling back into a gas. Hydrogen can also be stored on the surface of or within solid materials. Hydrogen can be stored by methods such as in the figure, as physical based and as material based. As physical based, compressed gas, cold compressed, and liquid H2. As material based, adsorbent, liquid organic, interstitial hydride, complex hydride, and chemical hydrogen. Materials-based hydrogen storage, as well as being compressed as a gas or stored as a liquid, hydrogen can be stored using materials. There are three types of hydrogen storage materials. Those that use absorption of stored hydrogen on the surface of the material, and those that use absorption to store the hydrogen within the material, and a hybrid storage which uses a combination of solid materials and liquids. On this page, I will tell you computational details. A custom package program was used in this study that using density function theory. Firstly, to calculate the formation energies by optimizing vanadium, hydrogen, lanthanum, cerium, and neodymium energy calculations were made for each separately. The crystal structure was formed by creating the FMM space group. Hydrogen atoms were placed at coordinates 0.5, vanadium atoms at 0, and rare earth elements at 0.25. Then geometric optimization of the compound was made by determining energy cutoff to be 600 electron volt and cut point set as 11 by 11 by 11. The lattice parameters of the optimized unit cells are given in table 1 and table 2. The calculated electronic band structure and density of states as electronic properties have been obtained for each situations. Elastic constants, bulk modulus, Young modulus, shear modulus, and Poisson ratios were determined for mechanical properties. We see here crystal structures of V4H8 and V4H8R alloys or compounds are here lanthanum, cerium, and neodymium. The red ones are vanadium and the white ones are hydrogen atoms. Okay. Table 1 and Table 2 show the lattice parameters of the optimized atoms and compounds. As you can see, A, B, C lattice parameters. V0 is volume. You can see here volumetric capacities and gravimetric capacities. Table 3 bond lengths of V4H8 and V4H8R. Okay. The figures show distance between the atoms of the optimized structure. Here we can see the bond length between atoms. As you can see, figure 3 and figure 4. Okay. Structural properties. As can be seen from the tables, it was observed that the volume of the pure V4H8 unit cell changes with the contribution of rare earth elements. Volumetric capacity is inversely proportional to volume, and the gravimetric capacities are inversely proportional to the masses of the rare earth elements we add. The bond lengths between each vanadium atom and the doping atom are shown in table 3. The bond length between R and H, all the doping atoms on the hydrogen atoms is longer than the between V and H bond lengths. The reason for this the increase in unit cell volume with the contribution of rare earth elements. Between R and H bond lengths decrease as lanthanum, cerium, and neodymium. Okay. On this page, I will tell you electronic properties. Bond structures, partial density of states and total density of states were calculated for each alloy to obtain information about the electronic properties. It was understood that alloys showed metallic character because the conduction bands were coincident. It was observed that the total density of states around the Fermi energy level changed according to the rare earth elements we doped and from which orbitals the contribution came from. It is seen that the metallic properties of the alloys originate from the F and D orbitals of the Re elements we doped. Since the bond length between the doped atom and the hydrogen atoms is longer than the bond length between the V and H atoms. And there is also no polarization of the f orbitals of the Re atoms. There are no H states opposite the Fermi energy. This causes the hydrogen atoms closest to the doping atom to oscillate in principle. Figure 5, we can see here partial density of states and total density of states graphics of V4H8 compounds. Here, blue line is here. Blue line is the orbital of vanadium atoms. Figure 6. By looking at total density of states and partial density of states, it is seen that the
Dear Chair, the video is over.
It hasn't finished yet.
Yes, and I think it's missing.
Right. Okay.
Speaker is here, Hüseyin Tavukçu. And can be
Well, so far I have a question. I think it's not finished, but I have one question until now. Is the speaker here? Hüseyin Tavukçu, are you here? Can you hear me?
Yes, I'm here.
Okay, I think your presentation is incomplete, but so far I have one question. Have you calculated the gravimetric density of these vanadium complexes?
Yes, I have calculated gravimetric and volumetric capacities. Yes.
Were you going to mention about that, because we haven't seen that?
Because my time is
Right. Can you tell us what are these gravimetric hydrogen density of these materials? What percentage? If you have that in your presentation, if you have calculated that. And we also have another question. One of the listeners is asking if you can estimate the hydrogen energy storage from DFT calculations. You can estimate that from by calculating the gravimetric hydrogen density or volumetric hydrogen density. You can estimate hydrogen dehydrogenation temperature and pressure and these theoretical calculations, and you can estimate the host materials structural, electronic, and thermodynamic and other magnetic properties. But you need, these are the theoretical calculations. You need to do actually the experimental studies to confirm these calculations, because theoretical and experimental, both of them are two different things. So I hope that answers your question, because the speaker is not going to be able to answer that.
I'm sorry.
Is that
my...
answer your question, Professor? I can't see your name.
My intent is
right? Is that answer your question, Professor Gomri, if I'm reading that correctly?
Unfortunately, my internet connect is unstable. Unfortunately.
Right. Okay. Thank you, Hüseyin Tavukçu. Thank you for your presentation.
I'm sorry.
I can reply it. I am Yasemin Çiftçi. we have calculated gravimetric capacity and volumetric capacity also, but this study is included dehydrogenation of using the lanthanum, cerium, neodymium atom. And we calculated gravimetric capacity, but we obtained very low value. We are continuing this study. We should check these results. So this result is not enough.
Right. So these are the preliminary results. Okay.
Yes.
Okay. Thank you. We have one more question from Professor Gomery, if I'm reading it correctly. Can you hear us?
Yeah, no.
The professor is asking if the author can estimate the hydrogen energy storage from DFT calculations. And I answered that question for him or for her, I'm not sure. I'm asking if the professor is satisfied with the answer.
Okay.
Well, so we cannot take it, right? Anyway, so let's move on to the next speaker. Our next speaker is Kerem Bülbül from Istanbul Technical University from Istanbul. And the presentation title is The Transition of the Natural Gas Power Plant into the Methane Pyrolysis to Hydrogen Power. So we are listening to you.
Dear Chair, I am staff.
Yes.
The speaker is joining with a video and I will share it.
Yes, go on, please.
Hello everyone, let me briefly introduce myself. My name is Kerem Bülbül. I have just graduated from Ege University Chemical Engineering Department and currently I've been studying at Istanbul Technical University for my Master's Science and TÜBİTAK as project scholar simultaneously. So my interest with hydrogen comes from its nature. Having a glance at the universe, we can easily see what it covers, such as water and sun. Since I meet with hydrogen, I always try to visualize it to use it in our industry. As you know, today 98% of hydrogen is produced from methane reforming in the world besides its repercussions. I hope the organizations just like this will assist the usage of clean technologies for hydrogen production. So I'm quite pleased to be part of such kind of organizations. So as a production method, even though fuel cells account for highest potential as a clean hydrogen source, it is infeasible considering next decade to be able to produce hydrogen for industrial amount. There is a reason to believe that if we can generate hydrogen for industrial amount, so we will solve our upcoming energy issues for our next decade. So let's commence our presentations. Today, I will talk about the possible transition between natural gas power plant and methane pyrolysis. So as an introductory, over the last decade, the demand of the natural gas has risen substantially and is about 200%. This spread has seen as a beneficial improvement in relation to CO2 emissions. So despite the fact that natural gas emits around 50% less CO2 than coal, it still does. So this is our issue. For instance, United States on its own has released 560 million metric tons CO2 from natural gas in 2019, and it's equals to annually 124 million automobiles emissions annually. So this is the reaction of basic methane oxidation. So as a product, we process CO2 or less. This very day, over 20% electricity generation in the world is produced by natural gas. So this is why we focused on this area. So this is the fundamental view of natural gas power plants. So the point is, what will you thing if we told you that there's a technology that can turn this view into this view. So let's see the introduction. The pyrolysis is the thermal decomposition of materials at elevated temperatures in absence of oxygen. This technology has recently come to the fore with the aim of producing synthetic fuels, various chemicals from biomass and waste. However, volatility in biomass and in coal complicates the pyrolysis process because your feed loses its mass as much as its volatility amount. So for this reason, methane, which has virtually no volatility compounds, can be the best alternative to be pyrolyzed. So this technology relatively new process, and if it uses electricity, and if you use this electricity from renewable sources, there are actually no greenhouse gas emissions in this reaction process. This is an idea that existed since the oldest years, but has generally failed due to technical implementation. However, so this, as you can see, methane decomposes through solid carbon and hydrogen. We know hydrogen, what it is. The carbon black is a raw material used in various sectors, especially in tire production process, and its price may vary between $700 and $1,000 per each ton. So this is our flow diagram for our design. So let's commence with reactor. Generally, if there's a reactor in a process, so we deem it as a heart of the process, just as here. So it's very crucial for us. So as we mentioned, the reactor is a plasma reactor, which absorbs energy not for the temperature increase, but chemical change between molecular bonds. So if we compensate this electricity from renewable energy source, we can distinctly say that we possess zero emission process. So it enables this, as electricity need for the reactor is 1/3 of the plant capacity. This is important. For instance, today it's tough to supply 14 megawatt electricity from renewable source, but 13 megawatt electricity can be precisely supplied. By the way, this is not the scope of this study. It may be examined in the upcoming studies. As you can see, we have hydrogen here and carbon black here is a product. So this process works generally for the aim of carbon black because in the product dispersion it possesses 3 times higher carbon black than hydrogen by kilogram basis. So however, what we thought is because of the cleanness of the process, if we increase the feed, hydrogen amount will increase inevitably. So thereby we adjust our feed to produce amount of hydrogen that compensate our electricity requirements. So as you can see in the on the upside, hydrogen goes through gas turbine to generate our electricity requirement. So the crucial thing, maybe it's as an obstacle, is a gas turbine. Because there are questions: will they be able to burn hydrogen to generate electricity in gas turbine? Because this new technology, is there a gas turbine that can accomplish this? So generally, we have seen that in our current technologies, the mixture of hydrogen with methane is burned in gas turbines to produce electricity. This is relatively common technology. So, but the turbine that enables the burn over 30% hydrogen content, it's restricted. The companies such as General Electric and Mitsubishi Hitachi Power Systems have been working on burning pure hydrogen in turbine. In figure, as you can see in figure 2, this is an example from South Korea. There is another example in Italy. So these are the available technologies to be adapted into our project. So we took them as a reference in our analysis, in our calculations. So as a method, we picked life cycle assessments. In the literature, what we see is in these kind of analyzes, especially for power to gas projects. So this method will make your will make your job easier. It provides better understanding for your analyzing. So that's why we picked it as a method, our analyze method. So from deductions, the deductions from our study is like annual additional income. We found that 195 million Turkish liras. So operational hydrogen price was calculated 1.68 dollar per each kilogram. It is very close to its alternatives, which is methane reforming. So as a payback period, while the payback periods of cogeneration systems driven by the gas engines are between the range of 5 and 2 years, we have found that 3.49 years of payback periods. So as a environmental impacts, we have saved the amount of CO2 116,614 metric tons CO2. What does it mean? It equals to roughly 25 dozens automobiles emissions annually. Also it equals to annually 4,800 planes annual emissions. So this is the huge amount, as you can see. So we analyzed 3 cases. While the first case represents the existing case, the third case also the existing case, but we added the carbon capture utilization to be purified our emissions. So we saw that this purification cost, as you can see in here, difference from there is a difference from it. So in all cases, we produce the same amount of electricity for our power plant. As you can see, it's 40 megawatts our electricity. So in the second case, it's our favorable. It's our case, the parallel case. So in this case we increase the natural gas amount, so almost 3 times higher than the alternatives. So while we do this, we produce hydrogen and carbon black, and we produce an electricity from hydrogen, and we also gain income from carbon black. So this represents this cause additional income, annual additional income, save for our electricity needs. So this income is per year roughly 200 million Turkish liras additional incomes was revealed. So we have derived net present value versus time figure as you can see, and this is the cash flow by taking a discount rate of 3%. Since our study is not a startup but transition, we didn't take into account other expenses such as labor, maintenance, and the like for the calculation of investment cost. So as you can see, payback period time is shown here. So as a challenge, as a conclusion, 3 inquiries will be asked. 1, will the design plant be able to produce carbon black of that quality, whose price is $1,000 per kilogram? The quality of your carbon black is crucial in this process. You should produce that quality. So subsequent to, if so, can it be found to consumers who can purchase the produced amount of carbon black? This is also the issue. Last but not least, what are the safety limits of operation as per hydrogen usability? So for our study, we didn't take into account, for the simplicity, the safety limits of hydrogen obviously will bring about additional investment cost into your project. So overall, due to additional income from carbon black, the methane pyrolysis plant is economically more advantageous than the natural gas power plant. Furthermore, the methane pyrolysis plant possesses a relatively short payback period, considering the factors such as payback period, calculate hydrogen price, carbon black income, and absence of CO2 emissions. Transition of the natural gas power plant into methane pyrolysis plant might be feasible. This was the last page of our presentation. Thanks for your attention.
Okay, thank you very much for the nice presentation. Are there any questions? Well, I have one question. At which temperature this methane pyrolysis happens?
Thank you too. It's above the 1000 degrees Celsius.
1000 degrees Celsius. Wow. And
Yes.
I realized that you did your calculations based on you are having a pure methane. So where will you get the pure methane? Where will you get it?
What does it mean by saying this? I didn't get it.
You did your life cycle assessment. You
Yes,
did all your
yes,
calculations based on that you have pure methane
Based
that
on
that goes into the methane pyrolysis. Then you got carbon black and hydrogen.
yes.
For this reaction to be true, you need to
Yes.
have pure methane that needs to go under pyrolysis. So where will you get this pure methane?
Yes, I get it. As a calculation, we assume that it's pure. However, the purification or also the impurities in the natural gas, as my view, I haven't searched for it, but as in impurities, it's okay to use for this process. But as I said, I haven't searched for it. If can it be done?
Well, for this study, for you to use pure methane, you need to either use coal or natural gas, or maybe other sources, I don't know. And then you need to get pure methane by gas separation. So that adds extra, expense and experiments on these calculations. So I think you need to consider that too. Anyway, thank you very much for your presentation.
You're welcome.
Are there any other questions? Okay, our next presenter is, I'm sorry if I'm not reading it correctly, Keiicho Sawahara from Graduate School of Engineering, Japan. And the presentation title is Early Stages of Mechanochemical Methanation over Lanthanum Nickel-Based Alloys.
Dear Chair, the speaker is joining with a video, and the speaker is here.
Okay. Can you hear me?
Yes, we can hear you.
Okay. Hello, this is Keito Sawahara from Graduate School of Engineering, Tokyo University in Japan. Today, I'm talking about this title, Early Stage of Mechanochemical Methanation over lanthanum nickel-based hydrogen storage alloy. Okay, this is my introduction. Recently, we have been consuming a large quantity of fossil fuel. Therefore, CO2 concentration in atmosphere is increasing rapidly, and the global warming issue has become our great concern. So we should reduce CO2 emission. Then CO2 methanation has been suggested like this figure. Hydrogen is enough to characterize as energy, but hydrogen has many issues. For example, hydrogen enrichment needs to be measured. Fossil fuel is high cost, and infrastructure development is necessary for hydrogen. However, methane is main component of natural gas. Therefore, we can use current infrastructure as it is, and we can use atmospheric CO2. CO2 methylation reaction is known as a substitute reaction, but this reaction needs high temperature and catalysts like nickel. So other energy saving process are desired. So in our previous study, we tried an alternative process for mechanochemical methylation over lanthanum nickel hydrogen absorption, hydrogen storage alloy. We confirmed that the methane generation successfully without any external heating, and after the Boroming sample showed the phase separation and phase separation which lanthanum and lanthanum oxide, lanthanum carbonate, and nickel. Moreover, atomic hydrogen supply from alloy was suggested. In this study, we attempted in situ monitoring of the pressure during mechanochemical process and the investigation of microstructure which might have contributed to the mechanochemical methylation. Okay, this is my experimental procedure. We modified the structure of the setup. We connected the vibratory warming with the homemade type GPS apparatus. By this, we can monitor the pressure during the mechanochemical process. We use stainless steel bore and stainless steel wire and sample powder, which lanthanum nickel 5 and the lanthanum nickel 4.6 are now 0.4. This is hydrogen storage alloy powder, and we injected the gas, hydrogen, and CO2 1-to-1 ratio. We carried out the gas compression analysis by gas chromatography. We characterized before milling and after milling sample using the SUM and the EDX, XRD experience. Today's we especially talk about the SUM and the XRD result in this presentation. This is a gas composition analysis by gas chromatography. At first, by atmosphere was only hydrogen and CO2. We confirmed the methane generation after milling for 2 hours. Moreover, CO2 completely disappeared after milling for 24 hours. Further warming resulted in even more methane generation with increasing the warming time. This result hints at the formation of carbonate. This can be carbon source for methane generation. In the course of this milling process, the pressure was monitored after milling for 1 hour. Pressure was suddenly decreased, but the pressure increased temporarily after milling for this area. 2 hours, 4 hours, temporarily increased. Next, we are going to focus on this blue area. We calculate the reacted gas amount during the CO2 methylation reaction from the gas pressure and its composition determined by gas chromatography. Characteristic pressure drop in the array period was caused mainly by hydrogen. After milling for 18 minutes, hydrogen amount decreased. This could be due to the hydrogen absorbed by lanthanum nickel 5 powder. Regarding the pressure increased during the 120 minutes to 270 minutes, once observed, the hydrogen could be dissolved. At this period, we confirmed the methane generation. But why did hydrogen dissolve to this area? Next, we will show you SEM images. The silver sample particles shows about 75 micrometer, but after milling for 15 minutes, particle quickly pulverized down to several around 10 micrometer. But for the beginning result, particle size reduction only to the same extent. After meeting for 80 minutes, hydrogen pressure drop was observed, where particle size reduction was also significant. This is X-ray diffraction results. In order from the top, after meeting for 15 minutes, 45 minutes, 80 minutes, 155 minutes, and 224 minutes. After meeting for 15 minutes, samples still showed nickel 5 powder. Nickel 5 pattern. But after meeting for 45 minutes, the sample observed the trace of phase decomposition. Moreover, after meeting for 18 minutes, peak pattern showed nickel lanthanum oxide, and straight lanthanum nickel 5 peak pattern. This red triangle is lanthanum nickel 5 pattern. Blue star is nickel. Green circle is lanthanum and lanthanum oxide. Okay. After meeting for 150 minutes and 224 minutes, only showed nickel and lanthanum oxide peak pattern. This result showed lanthanum nickel 5 had hydrogen storage property, but lanthanum nickel 5 occurred phase decomposition to lanthanum and nickel due to the ring effect. Therefore, sample lost hydrogen storage property and dissolved content hydrogen. As we discussed the beginning, we observed the formation of methane when hydrogen partial pressure increased, suggesting the supply of atomic hydrogen contributes to methanation. So this is gas composition analysis. This blue triangle and the blue circle. Blue triangle is hydrogen, and this blue circle is methane generation. Then we carried out the sample experiment of which using lanthanum nickel aluminum powder, the hydride dissociation plateau pressure of lanthanum nickel 5 is 0.3 megapascal. However, lanthanum nickel 4.6 and 4.6 aluminum 0.4 powder shows plateau pressure 0.02, 0.03 megapascal. The difference observed here in the methane generation rate and the hydrogen drop could be due to the difference of plateau pressure. From this result, also showed this hint at atomic hydrogen supply from alloy is key for efficient mechanochemical CO2 methanation reaction. This blue line is lanthanum nickel 5, green line is lanthanum nickel 4.6, aluminum 0.4. Hydrogen drop and the hydrogen increased, and the methane generation rate is higher than lanthanum nickel 5. This is my conclusion. As a result of in situ monitoring, observed the after meeting for 1 hour showed the plateau pressure. 1 hour showed the pressure was suddenly decreased, and after meeting for 2 hours and 3 hours, pressure temporarily increased. And the more exciting results showed after meeting for 80 minutes, the trace of phase decomposition observed. Lanthanum nickel 5 had a high hydrogen storage property before meeting, but phase decomposition was observed after meeting for 80 minutes. Therefore, the sample had lost hydrogen storage property and the hydrogen pressure increased at that time. This result, we suggested the hydrogen supply might be used for mechanochemical CO2 methanation. Moreover, we carried out experiment that use lanthanum nickel 4.6 and aluminum 0.4 hydrogen storage alloy. In this experimental showed methane generation rate and the hydrogen drop rate was higher than lanthanum nickel 5 hydrogen storage alloy. This result also showed atomic hydrogen supply is from subsurface from alloy is key of mechanochemical CO2 methanation. Thank you very much.
Thank you for your presentation. Are there any questions? Okay, thank you again. So our next presenter is Hatice Öner from Gebze Technical University, Kocaeli, Turkey. The presentation title is Hydrogen Generation from Hydrolysis of Alkali Sodium Borohydrate Catalyzed by Manganese Dioxide supported by Cobalt Chromium Boron Nanoparticles.
I am sharing now. Sorry. Okay. Dear colleagues, welcome to my presentation. I am a master's student of Chemical Engineering Department in Gebze Technical University from Turkey. Today I will present the topic entitled Hydrogen Generation from Hydrolysis of Alkaline Sodium Borohydride Catalyzed by Mangan Dioxide Supported Cobalt Chromium Boride Nanoparticles. In this presentation, first, a brief introduction to hydrogen energy and sodium borohydride will be given and then followed by the experimental and result sections of the study. Fossil fuels are not only harmful for environment, but also they will not be enough to meet the world's energy demand. These problems lead scientists to focus on new renewable energy technologies. Hydrogen is an energy carrier which has zero emission of greenhouse gases if it is produced using renewable sources. Hydrogen can be used effectively as a fuel in energy production by fuel cells. The other uses of hydrogen are also seen in figure. In order for the produced hydrogen to be used in desired places, it must be stored properly. At this point, safe storage of hydrogen is still an important issue that must be overcome. Especially hydrides are prominent hydrogen storage materials in terms of hydrogen that can be stored in unit volume, their reliability and lightness. Sodium borohydride is one of the hydrides with the highest hydrogen content per molar mass. When a suitable catalyst is added to the alkaline sodium borohydride solution, even at room temperature, hydrogen is released according to hydrolysis reaction. It is a simple and cost-effective method for the mobile applications. Noble and non-noble metals are used as catalysts for the hydrolysis of sodium borohydride. However, in these catalysts, there is an agglomeration problem which reduces the active surface area of the catalyst caused by the exothermic nature of the reaction. This problem can be resolved by two ways. First is adsorbing metal precursors onto the porous support. And second is doping of transition metals such as molybdenum, chromium, copper to the base metal in catalyst synthesis. These ways prevent agglomeration, increases the active surface area and also catalytic activity. In this study, our aim is to develop the effective catalyst for hydrogen production from sodium borohydride. For this purpose, manganese manganese oxide supported cobalt chromium borate bimetallic catalyst, which is alternative to high cost noble catalysts, are improved. For the synthesis of support material manganese dioxide, manganese sulfate was dissolved in aqueous solution of polyethylene glycol. Polyethylene glycol was used as surfactant to obtain nano-sized and porous material. Then potassium permanganate was added and resulting solid particles were recovered by centrifuge, dried, and then calcinated. Manganese dioxide supported cobalt chromium borate catalyst was synthesized by conventional simple and effective impregnation reduction method as shown in figure 2. Catalytic activities were tested in this setup. Alkaline sodium borohydride solution was fed into the temperature controlled reactor. Then definite amount of catalyst was added. During the experiments, evolved hydrogen volume was measured as a function of time by using gas burette. The morphological properties of support material mangan dioxide and the catalyst were investigated by scanning electron microscopy analysis. From SEM image, the manganese dioxide is in the form of nano-sized particle aggregates within the range of 150 and 250 nanometer. In the bottom of slide, the surface of cobalt chromium borate has interconnected nanosheet morphology with various weights. It is evident that cobalt chrome borate nanoparticles was successfully deposited on the support surface. In the energy dispersive X-ray analysis of catalysts, cobalt, chromium, oxygen, manganese, and boron peaks are observed in certain energy regions. Also, this peak belongs to gold, is due to coating material of the samples. Elemental mapping shows the homogeneity of species on the catalyst structure. The X-ray diffraction analysis of the supporting material matches the alpha manganese dioxide called Hollandite phase. As for the catalyst, the same XRD pattern was observed. This shows that cobalt chromium borate catalyst was in amorphous state. It can be attributed to the well-dispersion characteristics of active phase, which can be resulted in enhanced catalytic activity of the catalyst. Chemical oxidation state of catalyst was identified by XPS. Survey spectrum of catalyst in here confirm the existence of cobalt, chrome, boron, and manganese elements with corresponding binding energies. In the right side, the high resolution cobalt XPS spectrum indicates a set of spin orbit doublets along with associated satellite peaks. The difference in binding energies between subshells of cobalt confirming the existence of cobalt oxide. Similarly, high resolution chrome spectrum represented the multiplet splitting of the chrome 3+ cations. The high resolution boron spectrum can be fitted one main peak. The peak located at this binding energy could be assigned to the boron oxide species. Influence of chromium content was investigated by changing molar concentration of chromium per total metal amount. In the case of undoped manganese dioxide supported cobalt borate catalyst shows the lowest hydrogen generation rate than all other catalysts, and the optimum molar ratio of chromium was found to be 10%. The effects of sodium borohydride concentration on the hydrogen generation rate was investigated while the reaction temperature and sodium hydroxide concentration remained constant. According to the graph, the hydrogen generation rate increases with sodium borohydride concentration up to 15% by weight. Further increase in concentration, the rate of hydrogen generation decreased probably due to alkalinity, viscosity, and solubility limitation of both sodium borohydride, sodium metaborate, and sodium hydroxide. The influence of sodium hydroxide concentration was investigated with chosen sodium borohydride concentration here. Although sodium hydroxide concentration up to 10% by weight promotes the production of active components, higher concentrations from this volume may result agglomeration, which causes low catalytic reactivity. As a result of optimization, maximum hydrogen generation rate was found as 13.8 liter per minute gram catalyst. The hydrolysis of sodium borohydride was carried out various temperature. The increase in the hydrogen production rate depending on temperature can be seen in table 1. By using the hydrogen generation rates for 4 temperature points, apparent activation energy was calculated by Arrhenius equation and found as 36.3 kilojoule per mole. Stability of catalyst was determined by recycling the catalyst for 4 tests. At the end of fourth trial, almost a 75% degrees was observed in the hydrogen generation rate compared to the first trial. Table 2 lists the cobalt borate catalysts reported in the literature. Our study drew the attention because it has one of the highest hydrogen production rates among these studies and uses a simple preparation method such as reduction method. At the same time, as can be seen, it has a rather low activation energy value in compared with others. As for the conclusion, in this study, mangan dioxide supported cobalt chromium borate nanoparticles were synthesized by facile impregnation precipitation method. With the addition of chromium to the cobalt borate structure, hydrogen generation rate increased by 3-fold compared to bare cobalt borate catalyst, and activation energy value, which is quite low compared to the literature, was obtained. The reusability of the catalyst was determined as 75% of initial value after 4th run. The catalyst developed in the present study exhibits superior catalytic activity, stability, and lower activation energy. Therefore, it can be concluded that mangan dioxide supported cobalt chromium borate is a promising candidate catalyst for fuel cell applications. Thank you for your attention. If you have any questions, I will try to answer them.
And thank you for your presentation. Are there any questions? I guess not. Thank you again, Hatice. I would like to thank all the speakers and listeners. I think this afternoon session has finished. Thank you all for attending this session.